Actually, it's a few minutes after 10. So good. I hope the first test, if I'll call it a test there, went well for you. It seemed like for many of you it did. That's good. And anyways, I'll get a chance to look at them this weekend and get them back to you. Also, check your during this week. You might want to check your email box sometime this. Well, maybe I'll say it. Hopefully, I'll actually do it. But after I finally get your test graded and after I get them input, I'm going to send through Pipeline all of you a link to the grade sheet. If you recall, last semester we kind of switched our computer system, and I post grades then through the link that I'll send you instead of that default that I've been doing from our server. So I set it all up this weekend, and now it's ready to go. All I got to do is enter some grades and then send you guys out the link here. And so anyways, you can kind of look at it. So I'm hoping goes well is I get it graded, I get it recorded, and I send you the link. It'd probably be late in the weekend by the time I got it graded anyways, but maybe Sunday night you would see it, and you can kind of check your score even Sunday night or Monday, or just wait till Tuesday when I see you again, and then I'll pass it back. I don't anticipating having them done by Thursday. There's just not enough time to grade that many in time. It'd be awesome if I did, but I know that's not the reality. So I'll start this evening, and I'd be happy if I just have everybody's number one graded in these next couple of days before I hit the weekend. All right, well, with all that said, you know exactly what we did last time we met on Thursday is we got started with thermodynamics. We started with this beginning chapters. I hope a lot of it was review and beginning stuff like the different temperature scales. We talked about Fahrenheit and Celsius. And so we've got and Kelvin, and we've got a few more discussions to have in this chapter. But again, I think you will find, if you haven't had a chance to read the chapter, which is kind of understandable, I'd encourage you, read it now. And we're going to kind of wrap it up here today, at least maybe the lecture part of it. I'll do some examples for you then on Thursday, and we'll get started into the next chapter. All that is to say is I think you will find this chapter 19 pretty straightforward, a lot of review, stuff you've already seen before. However, important leading into the next chapter. So I would encourage you to read chapter 20 before you come to the lecture then on Thursday, because now you'll start seeing some new things, some things we did not do in Physics 102 or until we had calculus. And so our thermodynamics, of course, is going to start to get a little more advanced as we get into chapters 20, 21, and then 22. Wow, by the time we get 22, it's pretty advanced. I suppose the good and bad news is we leave it there. We finally get to some really good stuff and we leave and we go off to optics. So just like we did with our waves. Well, like I said, a few more things that I want to show you. So I will start back here. I will ask this question, as I've mentioned before. Your author kind of waits a little bit later into the next couple of chapters before he starts getting into the molecular motion. But I think it's wise to start it early and to start it now here. And so I'm going to show you this again. I'm going to turn on the little BB bouncer, we like to call it, and take a look at this and just ask this question. Keep this mental picture in mind that those BBs bouncing around in there, and I'll shut it off because it's kind of noisy, but those bouncing BBs, those are supposed to be molecules bouncing around. And we left with this idea. I had that long rod across here, and I was heating it up. And I was trying to get across to you, what is the difference between something hot and something cold? Well, if it is hot, what happens? Yeah, the molecules are moving faster. And a consequence of that, as you said, it gets a little bigger. And so, having a mental picture, I think, helps. Here's something that's cold, and then if I warm it up, it gets a little bit bigger. The molecules move a little faster, they hit a little harder, they need a little bit more space. And of course, what you saw last time was the rod that I heated up. You might even remember that sphere and the ring, and I stuck it through the ring and I made this sphere bigger. Even tried to show you that when I warm up the ring, and maybe I should ask again, when you warm up a ring, the hole in the ring, does it get bigger or smaller? Yeah, the hole does get bigger. And so think of it as being material in there, because some of the homework questions you'll be asked to do is to calculate how much bigger is the hole. right? And so you're going to have to go, well, wait a minute, there's no material there. But it's the equivalent of material there. And that's where we want to get started here. That's where we left off. We have only showed you conceptually the idea of the expansion. We haven't shown you how to calculate that. And that's where we're about to begin. But I thought I would begin by just showing you some ones that I didn't have enough time here to kind of do at the beginning. I like your author's picture number 10 here. He does a good job here of, where is 10, of giving you one example here. It's about partway through the chapter, and he says, look, what would happen if? And he uses it as a mistake. I'll throw it in as something even more useful, but here he's got a steel bolt and a brass bolt, and there's a small gap between them. And so maybe this is an electrical panel and this is an electrical panel, and maybe they're not supposed to touch. But what happens when this gets warm? Yeah, they expand, and this small gap will close in, and as they come together, they could touch. So obviously we could have a malfunction because of the thermal expansion. Or this could be more legit in the sense this is what we want to happen. We want contact to be made. You know, maybe this is the inside of a room, maybe a computer network, and we don't want that computer network to get too warm. And so we have this here, and when those two contact, then red lights go off, air conditioning kick on, and all kinds of things occur once those two metal pieces come together. Question? No? All right. What?
Oh wait, the question. I think it was like, wouldn't it, if it was electrical, wouldn't it arc?
Arc would depend on A, how big is the gap, and B, how great is the voltage.
Because it looks a bit micrometers, it looks like it might arc quite well.
Yeah, but this could be a 1 volt situation, just enough to trigger that there's a connection. So you put 1 volt so it doesn't arc, and then when it makes contact, then that. Yeah, fair enough. Well, looking at another picture here is number 7 here. Here's a pretty good one too. Here is this, I think, is probably more realistic and more important, especially for those you go into either a civil engineer or a structural engineering here, is what's going to happen to this bridge or this building when it heats up. It does get bigger, right? It does expand. And so your author put this one, I don't know if you've ever noticed it here, but this is supposed to represent really a hot day. Maybe this isn't as good as picture as some of the other ones I've seen. But if you'll see, this is one edge of the bridge and this is the other end of the bridge. Or maybe I should say the anchor. In other words, the bridge looks something more like this. Here's the land. And you take and you mount these steel beams in it. The other side then is mounted on maybe a little roller, if you will, with a kind of a zigzag pattern for the road, so that when I then match the zigzag pattern mounted here, what that allows is when this whole rod of the bridge gets warm, what's going to happen to that bridge? It's going to expand. And so the edge of the bridge, one end of the bridge is mounted, that's this side, but the other bridge is put on a little roller, and so as the day warms up, the bridge moves into and fills in that gap. And then when it cools down at night or in winter, it's going to pull back. And that's nice to have the little zigzag instead of this. Otherwise, there's a big gap that, you know, tires and things fall into here. So you keep care of the gap, but you allow the bridge to get bigger and smaller. And without that, I mean, what would happen if you didn't build a place for them to expand? Yeah, it could crack, or it'll definitely expand, but it might expand in a sense that it would expand and then the bridge bows sideways or bows up. Either way, not a good situation. In fact, a picture of that, jumping down here to the bottom, here is smaller picture. Let's see, can we magnify this a little bit? Oh, it's kind of grainy. Maybe that's a nice balance. But here is an example of a railroad track that is, of course, supposed to be straight. When you lay the railroad track, you should put one trail or one rail down and then a gap and then another one. Why the gap? Yeah, so it can expand during the day and get, closer together and further apart and still be a nice straight line. If you don't leave a big enough gap, what's going to happen? That's what you're looking at here. The rails expanded. They then butted up together. Now they got bigger. So in this case, they twist left to right. You have a homework problem that has concrete buckling. And the concrete has, are laid in sections, and there's a small gap, and it closes up. And then it still gets warmer. And so the concrete bows up. And so the road does this. And you're supposed to calculate how high the road has lifted up on this hot day. Yeah.
So what from an engineering standpoint, which is the best time to work on making a railroad track anyway? At that when it's hot or when it's cold? Because if it's hot, you can place on the already expanded railroad tracks, and you can place on the already expanded railroad tracks.
Well, no, you just need to know what the temperature is that day or that particular hour that you're working and put in the appropriate gap. So the gap is calculated from an engineering point of view. It says, okay, we want this much gap to be there when it's, say, we'll predict that maybe someday it will go down to 32 degrees in Santa Barbara. And maybe on the hottest day, I don't know, 95. Maybe we better engineer it to 105, or maybe we can engineer it to 120, just in case it gets 120 on that part of the track. But you can ask yourself, and we'll go through the numbers, what is the expansion difference between, say, 120 degrees Fahrenheit and 32 degrees Fahrenheit? And say, okay, that's the gap I need to leave in there. And if you're laying the tracks when it's 32, then you leave that full gap. If it happens to be 70 or 80 degrees that day, then you have a different gap. Now, I pick on Santa Barbara. There's an interesting story behind Santa Barbara because if you look carefully at the layout of our streets from State Street on out, they're so close, I don't think you would recognize it unless you were looking at a map, but they are slightly different in length from road to road because when I wish I could remember what year it was, but they used to lay out lengths with a chain, a literal metal chain, and you'd stake it into the ground and go out the next distance and drive the stake and say, okay, there's the next street. And then you put another one chain and you go out to here and you go, that's the next street. And that's how you get even-sized blocks. And the weather changed dramatically when Santa Barbara was laid out right after... No. When did they lay out the streets? It was before California was a state, but it was after it changed hands from Mexico to United. So it was like 1848, 1849, somewhere in there when they laid it out. So interesting history behind there. I was going to go to the more extreme case. Anybody recognize maybe this picture?
Wait, was it designed that way, or was it that way?
No, that is actually part of the design. Because again, what would happen if you built this giant, enormously long pipeline that extended from one side of the United States to the other? They don't exactly say where it is, but the next picture is showing the Alaskan pipeline. So I'm going to say it's the Alaskan pipeline, which extends from the northern part of Alaska to the southern part of Alaska. One big piece of metal, if you will. Well, what happens when it gets hot?
Does it ever get hot in Alaska?
Well, okay. But during a summer in Alaska, it gets hot. But more than that is there's hot oil running through there. I mean, how do they send the oil through there? They dig it out of the ground or they pump it out of the ground. Then they get it blistering hot and put it in the pipe and it flows through. So yeah, that pipe does get hot. And then it can cool down though. And so isn't the size of it going to change? And it's every molecule, and that's what I want to emphasize as we get into the math here, is that how much it expands. Well, if you had 1 meter, you would have, however many trillions and trillions of atoms expanding. What if you had twice that amount? What if you had 2 meters? Wouldn't it expand twice as much? Because every single molecule expands the same amount. So if I had 1 meter, and 1 meter expanded this much, and then I took a 2nd meter and hooked it onto it, the whole 2 meters expands twice that. So the amount of expansion would depend on how many molecules I have, as well as what temperature it is. Fair enough? And so in a minute we'll get into the math, and that's what I want you to see. The amount of expansion depends not only just what is the material and what temperature is it, but also how long it is. And so something like this is really long, and that's what that is designed to do. So this pipe here that maybe now extends out for hundreds of miles, what happens when it gets cold? Well, it's going to contract, and what will happen is this will pull out, and this big arch will look more like that. And so this takes into effect the thermal expansion of that pipe. You can't do it like the railroads where you just leave a gap in there. You can't make a pipe, make another pipe. You gotta make a connection between there, and that is the design here of this pipeline. Yeah.
How do they manage the changes at the two respective factories where it's both leaving and then entering? And what is the engineering design for that, for a company for the kind of change in the length of the pipe?
See, if I understand your question, this is it. This is between one place. Let's say we pump it over here. And let's say we put it in a terminal over here for the ship to come in. This is in the middle so that the pipe can change its size. Is that what you're asking?
So they don't do anything at the end side for it?
No. Why? This is what you might call slack, if you will. Without putting a gap in there. It's really noticeable, unfortunately not where we live, but if you have telephone lines in the winter time, you will watch how tight they are, and in the summertime how much they droop. There's a big difference of their droop in the summer than in the winter. And again, not here in Santa Barbara, but but in places where you'll have ice hanging from them, you'll see how tight they are. And then it'll switch into summer and, be 105 degrees on Nebraska, and dipping down. Be a big difference. Yeah.
So does that mean like every couple 100 miles, so they have like these and then rollers underneath so they can...
Yeah, or it's certainly not the only solution. Your author shows you this one. This is one of my favorite pictures. This is actually the Alaskan pipeline. Okay. That other one I don't think so, because usually when you see the Alaskan pipeline, you see it elevated on these stilts here. Okay. But in this case, the way they've taken it is, notice the zigzag pattern. Kind of the S's through the wilderness. Because now when it gets warm, it gets a little longer, and so the S has bigger bows to it. And then when it gets cold, then the S tightens up. And so they have room for that. And so you can kind of see how this pipe is resting on a cross beam, which has rollers on it. And so it can move back and forth. And if I remember right, I think they designed that to move 3 feet back and forth as the temperature changes. Although it's also designed to roll back and forth for earthquakes too. So I think they designed it for 1 foot of motion, if I'm remembering the number right, due to thermal expansion, and 2 feet for earthquake vibrations. And so they got 3 feet of motion in there. Yeah.
That's a really big pipe. Can it slide back and forth really easily?
No, it's not that easy, but again, you're talking about a lot of forces here, right? These are molecules. These are, forces that push on each other. I mean, this would be like if you think of all those molecules in those pipes, it would be like the same as a solid metal piece, right? I mean, if you took a metal beam that was 2 feet thick, wouldn't you think that was a strong beam? And you'd say it's a strong beam because all those molecules are doing the pushing, right? So the same thing would occur for all of this oil in there. It's going to push and force. These are not small forces. There's no way you could like wrap a piece of metal around it and say, it's going to want to get bigger, but I'm going to trap it inside. You're not. It's going to get hot and then break the pipe.
So there's no way to artificially create that scenario?
What scenario?
Where you have an object that wants to expand, but you're forcing it not to?
No, I mean, I guess you could. You could. I mean, I could take, say, a piece of aluminum this big, okay, and realize that as it expands out, I just need to realize it expands out with the same force as a piece of aluminum that big. So I can't hold it with my hands. And I can't even wrap, say, aluminum foil around it. And I probably couldn't even put a steel case that is 1/8 of an inch thick. I probably could put a steel case that's 3 inches thick.
So what happens as it pushes, but there's nowhere to go?
Well, it'll tear the material.
And
If it's strong enough. If it's not strong enough, then it does. I mean, that's what you're really asking. If it's strong enough, it'll tear the material.
and if not,
Then it won't expand. Right.
then
Right.
what happens? Like it just deals with it? I mean,
Well, it's no different than anything else under pressure. It would be there until what? Well, until you took it out the pressure, then it would get bigger. So you just physically put the molecules close together. Geology is probably a really good example of that, especially here in California, the whole Sierra Nevadas, and particularly Yosemite, where those rocks were deep underground under a lot of pressure, and then they cooled and they hardened. And so they have a size to them. Now they were deep, and so as they came up and as the erosion wore them away, they kept getting bigger, and that's why they're cracked today. So when you go and see any granite that's exposed to the surface, you don't see this giant monolith of one solid piece of granite. It's got cracks in it, and those are there so that we can rock climb. No, those are there because of the expansion, and then they separate it out and they expand it. So that's nature expanding. And geology can be big difference. I mean, a rock can be half the size or twice the size on the surface as it was when it was formed down miles deep. A lot of pressure.
When an object gets so hot that it starts to tear, is that just when it starts melting? Or
Well, right, and so maybe in that, yeah. So and then you'll notice here, I haven't got into the numbers, but when we start doing the numbers, they say, how are we going to calculate how much it expands? And in the bottom of it, they give a little disclaimer that says, this is the expansion that occurs at normal atmospheric pressure. And so that's really what we're talking about, normal atmospheric pressure. That's going to change. I'm glad you're asking in the next chapter. But for right now, it's just kind of the simplest case, just normal pressures. What would happen with this one? And really not part of this, but as long as we're doing thermodynamics, you can actually see the cooling fins on here too. That's kind of an added extra here. But this pipe is very hot, and the idea is to transfer, well, ideally to keep the heat in the oil so it'll stay warm and viscous and go on through there. But what we don't want to happen is the heat to conduct down and go into the permafrost of the ground and have environmental issues. So the idea here is the heat goes out overly up to here and doesn't, warm up the permafrost. So they have those heat sinks on there as well. But what it reminded me of then is my favorite picture, which is this one here. If you recognize this plane, it's the SR-71. More interesting, maybe I'll get a laser pointer somewhere in here. Can you see, the picture's not of real good crisp quality. Can you see those black stripes there? Yeah, that's jet fuel leaking. This plane flies so fast that as it flies through the air, it actually is a foot longer in flight than out of flight. And it's, I forget the exact number, I think it's 106 or 107 feet on the tarmac, and then a foot longer when it's at full speed. Okay, so it goes so fast, there's so much heating, there's so much moving of molecules, they get bigger. So the engineers are left in a tough position. How do you accommodate a change of a whole foot? And the answer is back to those railroad ones, is why don't we just leave a gap between everything? We'll build it, we'll put a gap between everything, and once you start flying, it will expand and fill up the gap. So what does that mean to the fuel tank, which happens to be inside the wings here?
It leaks fuel when it's on the ground.
It leaks when it's on the ground. So you put in the fuel, you let it leak. Just take off and fly. It'll warm up. And once it warms up, it'll close up. And then it won't leak anymore. And so this plane happens to be, I would assume if you are familiar with mid-air fueling, it's getting ready to drop down the boom right into there and refuel it. See, because it's been leaking fuel this whole time, and better get some fuel soon. Otherwise, it's not going to be able to go on its mission here. And so that, to me, that is just one of the bizarre approaches.
Couldn't you put the fuel inside of like a plastic container that doesn't change as much with the heat?
No, the plastic couldn't handle the heat, though. This thing's operating close to 2,000 degrees by the time it's in flight. So there's no plastic parts on this plane.
So how can the pilot exactly, never mind, it's transduction.
I would think with today's material we might be able to do this. Because remember, this is built in 67, 68, somewhere in that.
What about ceramics?
Ceramic shatter, so
They don't have flexibility. Yeah, I don't know.
As far as putting the fuel in?
Yeah, I can imagine the ceramics lasting. They'd get cracked. Or I'd have to make them thick enough they're heavy.
Yeah. I mean, like the vibration.
But
Cracks this
yeah, I'm assuming the design team, gave all those thoughts. But definitely do not want typically in an airplane wing you put a rubber bladder inside. And the bladder expands and contracts with that. But no rubber, no plastic if the outside temperature is 2,000 degrees.
Wasn't it a thermal expansion issue that caused the Challenger explosion?
Not quite. The Challenger one, it was a thermal issue. Its heat shields came off. One of the heat shields was knocked off during liftoff, and so during liftoff.
It wasn't something with it was really cold, so not the Columbia, the Challenger.
Oh, I might be mixing these. Challenger was the first one.
Right.
That's what you asked.
Yeah.
Yes, it was. Yes, sorry. Yeah, that's the one. The solid rocket boosters were put together. They were in sections like this. And yeah, the one section went inside another section, and they put O-rings around them to keep the propellant sealed inside. Yes, and it got, unfortunately, really, really, really cold and contracted. However, I think the bigger problem wasn't so much that the material got bigger and smaller, but the rubber, the O-ring seal, lost its flexibility when it got that cold. And so it didn't, as it got cold and then warmed up, the rubber did not expand back as you expect for a rubber seal to do. You make a rubber seal because when you clamp it on, you're pushing the rubber together. And then as the metal expands back as it warms up, the rubber always expands and keeps with it because the rubber is bouncy and rubbery. But it didn't do that because it was froze that night. Yeah. And then hot exhaust gases came out of that seal, shot sideways into the fuel tank, and eventually melted the fuel tank and ignited the fuel tank. Yeah. Well, anyways, I'll show one more, and we better get into the numbers. Here's one that's kind of related to some of the homework problems you will do, and some of the situations some of you will find yourself in a real world. Here's just a good manufacturing technique. What if you wanted to put metal pieces together, although this is a metal and a wood piece, but you don't want to weld them or make bolts for them? I mean, think about this. You warm up a ring. Here's a ring. What happens to it? It expands. So what if you take this ring and then you put it over a shaft?
It'll loosen up.
And then when it cools back down, what happens? Yeah, it tightens up, right? It clamps down. There's no weld points. There's no bolts. There's no screws and nuts and all those other things that have their own challenges and their own problems. And this is simply that. You warm up this and place it over the tire, and as it cools down, it just kind of clamps on. There used to be an outfit in town, and they were very proud in the end of Gulf War I because they made the axis for the Abram A-1 tanks. And not one of them broke during the Gulf War. And when I met the guy, or one of the engineers, when we were getting dry ice at the ice store, and they were getting it for the same reason, and he was talking to me about how they would cool down the shaft with the dry ice, and then they would put the rings over it, And then so when they would take it out of the dry ice bath, it would expand out, and there would be a nice tight fit between the shaft and the rings that they've added. And there was always some question about, would that be strong enough, as opposed to trying to weld things together or bolt them together. Putting holes into the shaft to make for the bolt holes kind of weakens the shaft. And so a lot of manufacturing, it does that. And so you can heat it and cool it. If you've not as common today, but if you ever watch an old movie, or the old Donald Duck movies, if you like cartoons. I mean, what's the big burly riveting guy? I forget his name there, but all the old cartoons, they've got the big burly guy on the bridge, and they're tossing him the hot rivets. What's the process of a rivet? A hot rivet. What are they doing? Yeah, and it's a pretty simple process. You take a long beam, you set it next to another long beam, and you want to join those two together. All right. So you drill a hole through the two beams, line up the holes, and then, I'm going to give myself a little more width to work with, but then you take a rivet. It's just a very, very hot piece of metal. It comes right out of the fire, and so the guy in the fire is stoking it as hot as he can, and his job is to get it out of the fire and up there to the riveter as quickly as possible, so it's still very hot. All right, so they toss it to each other with these metal catchers. But if you put then that rivet into here with the shaft sticking out here, and then you hit it real hard with a hammer on the other end to flatten it out. Now what happens when it cools? Yeah, it's like tightening a bolt here. And so as it cools, this gets tighter and tighter and tighter and tighter. And so a hot rivet can be a nice way of getting a nice, solid, and complete connection between the two based upon the thermal expansion. And again, that's kind of what we're looking at here. Well, there's a million other examples we can go into. Probably the most obvious one for the world you live in is, you ever check either the level of the water coolant in your car or the transmission coolant in your car? Particularly the water. If you've ever noticed, there is often the radiator and then a hose that goes to an overflow tank. Why the overflow tank? Why is it there? Because what happens when the car warms up? What happens to the water? It expands. It's got to go somewhere. And so it's designed not to expand and break your engine or your radiator, but it's designed to expand and go through the tube and into the overflow. And you can watch then the level get higher and higher in the overflow tube as your car warms up. And the reverse is true. What happens then when you park the car and it cools down? And then it, draws it back over the overflow tube and puts it back into the engine. And so that size difference is accounted for by the design. Well, I'll get into some numbers then here, and we'll get into some calculations. Maybe not today, but soon here. But one of the ideas here is then with thermal expansion, then things should get bigger and things should get smaller. And so I'm going to write here delta L. Maybe the notation is obvious, but I'll stop. What do you think I mean by delta L? Yeah, the change in length. So if I have a beam or some kind of metal piece that is length L naught, it's going to get bigger. And that's what I mean by delta L. Probably wouldn't surprise you if I put a delta T up here. What do you think the delta T stands for? Yeah, change in temperature. So as the temperature goes higher and higher and higher and higher and higher, what do you think is going to happen to this metal piece? Yeah, it's going to get longer and longer and longer. So that was the conceptual picture I was trying to get across here. But also, the one that maybe isn't so obvious is the original length. Now, some people prefer this. I think this is harder to work with mathematically, but it kind of makes sense when you're thinking of what are you really saying here? You're saying how much length increases per meter is a function of its temperature. And we're back to what I was saying earlier. How much bigger does something get depends not only on how much do you warm it up, but how much material do you have? Every atom goes faster. So if you keep this mental picture, if I have a 1 meter rod this long, okay, and I warm it up, and say it grows that much, then if I had 2 rods, then each rod, when I put them together, a 2 meter rod, each one would get that much bigger, right? And so the increase in length should be based on how much material I have. How long is the material? And then finally, the last piece of this puzzle is what your book gives the symbol here, alpha, and says this depends on the material. Some materials expand more than others. We will call this the coefficient of linear expansion. And that will be our working equation for how much bigger something is going to get, or in this case, longer, by saying it depends on the material, depends on how much material you have, and depends on how much you warmed it up. Kind of makes sense there, right? And in fact, I left the overhead on here because it's worth calling some of these numbers up and taking a look at them. Your author has shown you in Table 1 a whole slew of materials and looking at how much do they expand. Let's pick on aluminum since it's at the top of the list. Here's the material, aluminum. This is the linear coefficient of expansion. The number is 24 times 10 to the minus 6. What does that mean? Well, that means mathematically I would put here a 24 times 10 to the minus 6, but what it means here is 24 microns. Okay, let me call 10 to the minus 6 the micron. But it's simply saying that if I had 1 meter of aluminum and I warm it up 1 degree, it's going to expand 24 microns. That's what that means, right? Aluminum expands 24 microns for every degree, every meter, right? That's what that means. If I warm it up more than 1 degree, well, it's going to expand more than 24 microns. If I have more than 1 meter of aluminum, it's going to be more than 24. But a combination of those 3 factors. What is the material? How much do I have? And how much do I warm it up? That's how much it expands. So quickly on our loose list here is aluminum. Behind that is our brass and our bronze. And you can scan through here. They have the different materials and how they expand. Obviously what we were talking a lot is about a bunch of steel. So steel's about 11, somewhere about half of that of aluminum. And so we're building a bridge out of steel. We want to know how much bigger this bridge is. If this is the Golden Gate Bridge, it's going to get significantly bigger as it goes from one side of the other. Not so much that steel has a big expansion coefficient, and really not so much because the temperature changes that much. It doesn't change that much in San Francisco. It seems like it's always cold in San Francisco, but never snowy, right? I mean, it's, was it Twain who said the coldest winter I ever spent was a summer in San Francisco? And I didn't appreciate that as much until this summer when I spent 4 days in San Francisco in the middle of summer. It was cold. It was freezing cold. And what was really weird is I spent 4 days there, followed the next day to drive up to the gold country. I wanted to see Sutter's Mill and all of that. And so within 1 day I went from, I think it was 55 to 110 and got out of the car 4 hours later going, oh my gosh. I guess I didn't appreciate the cold weather as much. And I never even saw the Golden Gate Bridge other than, 10 feet, it was so foggy. But anyway, sidetrack there. All right, but picking on the Golden Gate Bridge because of this. And most bridges, because of this, they have a large L. And so the amount of expansion can be quite a bit. Not so much that their temperature changes that much, but because the length of it is very long as you extend across, in this case, the opening of the San Francisco Bay. And so it expands. But my point is, look at these. Now let's take another step beyond this. Hopefully it's obvious, but the world is not just one dimension. So if you warm something up, not only does its length expand, but what else? Doesn't its height and its depth, right? And so if we are looking at a three-dimensional world, we probably should extend this out. I mean, this kind of picture would be something like this, that if I started with a length of L naught, and then I heat it up, it's going to get bigger. And maybe I'll put dotted lines for it getting bigger. And so this is the delta L. And it'll be okay if I just draw it on one side. I mean, which side goes bigger kind of depends what you did with it. The example I did in class, I don't know if you saw, but I had one side mounted to a metal pole so it would expand that way and make that dial turn. So I'm just going to let it expand. I suppose if I just heat it in the middle, it would probably expand, you know, both directions. But the point is, this is the calculation for how much it expands. If I change that to something that looks like this, and I say, okay, here's a box. And I start here with a box that has some kind of height H, some kind of depth D, some kind of length L. And I warm it up. Well, what's going to happen? Well, I guess it'll expand in its length. But it'll also expand in its height. And it will expand in its depth. And so, what we will have is not just a length expansion, but a volume expansion, right? And so extending this on, we would have something that looks like this. We would say, what is the change in volume? Well, what do you think it would depend on? How much are you going to warm it up? What is the original volume you started with? And then some kind of an expansion, which your author labels as a beta, and says, look, it's going to get bigger based upon that material, how much it gets bigger. So again, still looking at this table, you will see that your author jumps over to here, and he has the volume expansion coefficient for beta. Now, if you'll notice, he only lists it for the liquids. He doesn't bother to list it for any of these solids. More on that in just a second. But that kind of makes sense. In fact, we already talked about it. They don't list, oh yeah, they do. Here we go. Here's mercury. This is the expansion of mercury. And we talked about this last time. Mercury is great for making a thermometer. You put it in, as the molecules go faster, it expands, and it's quite a bit. And so mercury will go up the column here. And fortunately, mercury expands more than the glass. Some people forget that. I mean, what would happen if you had a thermometer where the mercury expanded equally as the glass?
Never does.
Yeah, you wouldn't see a temperature change, right? You would hold it up in the air and go, well, the temperature is at 22 degrees Celsius. You put it into something hot, and now the spacing between them expands. But so does the mercury, and it still says 22. So you got to remember, we need something that go into the thermometer that expands more than the glass. Glass does not expand very much here, and you can see kind of the small number here for the glass, and hence mercury makes a good option. It's a liquid, and the other one is alcohol. Do they list alcohol up here? Oh, okay. And again, expanding quite a bit. One of my favorite is turpentine. Here we go. Because turpentine can really expand. And so we have a container filled with turpentine. Some of these float, some of these don't float. This is a thermometer. From your distance, you probably can't tell, but this little bulb right here says 74 degrees. That says 76, that says 78, that says 80, 82. This one says, must be 72. So I know this room temperature is somewhere between 72 and 74 degrees Celsius. What happens when it warms up in this room?
What are the bulbs saying because of water is less dense than usual? I think.
What are the bulbs?
So when it warms up,
The size of the vacuum decreases because the liquid expands.
the key is really the turpentine in here. It expands, right? And it becomes less dense. So what happens now?
Whenever a bulb sink,
What was Archimedes' principle? I know I'm going to take you back a chapter, but you probably already realized that when you did the bullet shooting into the block on your first problem. Hopefully you did conservation of momentum, not just energy, right? There's heat on the impact. Oh, I shouldn't tell you that. You're going to make you feel bad if you read that. Okay, but part of that problem was going back to physics 121 and doing a collision and doing conservation of momentum. Same thing here. Part of this problem is going back to our mechanics and going back to Archimedes' principle. We learned back in physics 121, objects float if they are less dense, right? So right now, if you look, these objects all float because they are less dense than these objects. And so these float, these sink. Each one is at a slightly higher density going down. As the turpentine either warms or cools, its density changes based upon thermal expansion. If we go with warming, what will happen is it will warm. This will expand upward a little bit. Probably not enough that you'll see a change there, but definitely enough that it will now be less dense than this one here that's floating. And it'll do what?
Sink.
It'll begin to sink. And so as the turpentine warms up, more and more bulbs begin to sink. As it cools down, more and more begin to rise. We'll see if we can see a change in these next few moments. We'll put it in ice water. And we'll let it sit there for a while. And it's pretty thick glass. It's not a very quick response thermometer, but it does work if you're willing to be patient and watch it. Yeah. Okay. And so there is our change. I actually thought it might be fun to actually see this. You can actually see the density. And so, only save myself a little bit of time here. Let me grab some ice water. Before class started, I put a balance up here with a hanging object. Now, the object, we're not worrying about what the object is. Watch what happens if and I need to steal a little bit of water out of here. So let me steal some water. Okay. Put that one back in there for a moment. See what happens in the few minutes we have left. Oh. No, I think I just bumped it. Because that one should stay up. It's the one below it. It should cool down and start to come up. But if you look carefully at this balance, you'll see it is not balanced. I have it set at, I don't know what it's set at, 60. So it's set at 60 grams here, all right? And these weights are equivalent of being over here. So this is pulling down at 60. What I can do is put this and look at Archimedes' principle. Archimedes' principle says the buoyant force is equal to the weight of the fluid displaced. Fair enough? And so if I've got this right, that is balanced. There is enough upward force from this ice water to make this balanced. Okay? What might happen if I took another beaker and this time hot water? Is the hot water having the same volume as the cold water? No. This hot water should be slightly bigger in volume than the cold water, which means what would you say about the density of hot water? It's a little bit lower. And of course we did that. Hot water rises, hot air rises, right? Because it's a little less dense. Which means then, when I put it in here, not worrying about the expansion of this one, which does happen, but let's just say that this changes more than that one. Okay, so I'll forget that this one changes. But when I put this into hot water, I claim that that hot water, now that it is expanded, is a little bit less dense. And being less dense, it will have less buoyant force. Is it balanced? No. It is slightly over. Now, not much, because granted, water doesn't change that much. It's not like the turpentine here, but I don't want to use turpentine here in the classroom. But if I just kind of move that over, there's about 1/2 gram. And the buoyant force has now changed a little bit as I went from the cold water to the hot water. And the buoyant force has changed because the buoyant force is part of the volume, it's part of the density, and that's part of our thermal expansion. And that's what I wanted you to see here. In fact, let's look a little closer at these numbers here. As I said, notice your author, when he asked you to calculate volume change, it made sense to do a liquid. What about the volume of aluminum? How come that's not listed here? All right, fair enough. Wouldn't you be able to figure out the volume change from really a length change 3 times? So let's give it a try here. If this was a block of aluminum, I would say this. What is the volume, and I'll say the new volume? Wouldn't the new volume be the length plus the change in the length times the depth plus the change in the depth times the height plus the change in the height? Right? Isn't that how you would calculate it? Let's do a couple steps of math. I'll take this out of the way so it's not blocking too many people's view. But as I go through a little calculation here, watch this. Here is length plus, and here's the alpha L delta T. That's how I get the change in length. What's this? D plus. And there would be an alpha D delta T. And then what's this? H plus. And then there would be an alpha, an H, and a delta T. So there's quite a bit of math here. Fortunately, most of those terms are so small, it's not significant. And in the couple minutes I have left, I will run through the math. I will also hopefully show you that those guys have started to rise. Probably, I wonder if I can mix up the cold with the warm without busting it. All right, let's see, hopefully that was enough mixing. But I want you to see what happens when all that turpentine is closed and it's more dense. They all should rise. That coldest one is at 64. Stopping there. So it looks like I cooled it down to an average of 64. But some quick math here. If I go L times D times H, that's L, D, and H all multiplied together, right? Then, as I do some cross terms, there's going to be a term where I have this term, the alpha L delta T, and that term times a D and an H. I will also have another term that will have an alpha, a D, a delta T times the L and times the H. I will also have this term, which is the alpha H delta T, and it would be times the L and times the D. Now that's not all the terms, but if you look here, what I've done is this term times that and that. There would be other terms, let me go ahead and work on those, like this one here, where it would be alpha squared L D delta T squared, that one times H. There would be another term where it would be, say, these two, alpha squared, an L, an H, a delta T squared, times a D. I'll stop there because we're low on time, but here's the magical step. Did you notice that this term had no alphas in it? These three terms had only one alpha in it. The next terms either have alpha squared or alpha cubed. Now how big is alpha? 10 to the minus 6. What happens when you square it? It's really, really small. So what we're going to do is an approximation. We're not going to do the whole multiplication. We're just going to drop all those other terms and get rid of them. And what we end up having then is the new volume, which you might define as the old volume plus the change in volume, would then be the first term, LD and H, plus, and look carefully at this, LD and H in every term. LD and H. LD and H. L, D, and H. What else is there? Yeah, once you factor out an LD and H, isn't there an alpha delta T just 3 times? And so this is 3 alpha delta T. And I'm hoping what you can see then in all of this is this is the old volume. This then is the change in volume. So the change in volume would be equal to 3 alpha times this guy, which is the old volume, times delta T. And be a good place to stop today as you get ready to do the calculations. You don't need to have listed in this table a volume expansion, because a volume expansion is what? It is a linear expansion 3 times. Now I ran out of time here, but what if the question was different? You have one on the homework. They say you have the surface of, and I forget what it is, let's say the surface of a quarter, and you heat up the quarter. How much bigger is the area? What do you think the change in a surface area would be? 2 alpha times the original area delta T. So whether you're talking about an expansion in length or an expansion in area or an expansion in volume, we only need it listed 1 time with a slight approximation in there. Okay? And liquids, we just do the beta because it makes no sense to talk about a linear expansion of a liquid. They flow whatever their container is. So we don't do linear expansions. All right, well, we'll stop there. It looks like there's a couple more things to show you, and then the example problems on Thursday, and